Okay, so let's talk trees. First, we'll do a summary of the simple data structures that we've already looked at. So far, we've stored data in arrays. So using kind of this natural behavior of the underlying RAM in your computer. So with arrays, we've kind of organized those. I almost always depict them with a sort of box diagram. And oftentimes I use the metaphor of like lockers at a gym or something where each item has an index, a number, and it can contain some value. We've also talked about linked structures using lists. So for lists, I've typically depicted those with some sort of a concept of a node. I've mainly focused on doubly linked lists where nodes have a next and a previous pointer. We've also looked at different access patterns, and these different access patterns could apply to things that use either an array or a linked list. So we've looked at access by index. So these are typically referred to as list-based operations. We've also looked at access by arrival time. So if you remember, that's where the idea of the stack and the queue come in. We've also talked about priority queues, which is our topic for this module, where things are accessed based on some additional property that indicates how important they are. So let's continue to look a little bit more at this idea of the linked list node, and we'll build on that concept a little bit. So the nodes in our doubly linked list contain a couple of different things. So I've been drawing them with these kind of circular diagrams. And oftentimes I break these diagrams into a couple of different pieces. So I'm just going to kind of highlight where I typically note these things. So usually the top piece is where I show some concept of a next pointer. So this is the component of our data structure that will somehow link to or refer to the next item. In a lot of ways, this is like a scavenger hunt, where this is kind of the clue. The next pointer or the next reference is a clue that tells us where to go to next. Typically in the middle of my depiction of a node, I put some sort of indicator of the data. So in a lot of the examples we've been doing in class, we've been using numbers. And then typically the bottom part is where I depict the previous reference. So this would be where there's some sort of a link that gets us back to the previous item, at least for doubly linked lists. Okay, so when we've been working with linked lists, conceptually and logically, they've been accessed linearly. So we've had nodes that are connected up to other nodes through this chain of next pointers, and then they also refer back to their predecessors through this chain of previous pointers. So we've drawn them out, or I've drawn them out, as structures that go kind of left to right in a line, and we've thought about accessing them using the ideas of like an index and accessing one item at a time from first to last or last to first. We also had the notion of a special thing that helped us keep track of the linked list. So we had some notion of a head. So we had some special piece of data that connects us up to the first node in the list, and then the nodes are chained together as we've described. Okay, so that's been a really useful paradigm, but now we're actually going to break out of it, and instead of dealing with things that are strictly linear, we'll look at things that can't always be drawn in a simple line as we've been doing. So we're going to expand on the idea of a node, and we're going to build towards a data structure called a tree. So first we'll start with the idea of a tree node. Now in this case, we're going to focus specifically on binary trees. So this is kind of a nonlinear, non-line-like way to store data. We'll use this concept of linked nodes. So for now, we'll continue to use this idea of linking things together with references. Later on, as we're talking more about different forms of priority queues, we'll see that there are, in some cases, ways to get around this and go back to using arrays. So I want to look at the idea of what a binary trees node would look like. And then we'll talk about some common terms that come up when you're talking about this notion of trees. So I'm going to draw nodes very similar to the way I've been drawing them all along. I'm just going to break it into a few more parts. So I'm still going to kind of break it up into the data part in the center of my node. Okay. But this top part I'm now going to use to refer to the parent And we'll come back to what I mean by parent in just a minute. So I've got the parent part at the top, the data part in the middle, and then I'm going to break the bottom part into two pieces. And this is where we depart from the linked list node. So I'm going to have one part that will connect up to something to the left, and another part that will connect up to something to the right. And typically the parent we kind of think of as connecting to something up above. Okay, so our nodes are going to be connected up in kind of this triangular pattern with a parent, a left child, and a right child. Okay, so notice that terminology, parent, left child, right child. You also see this terminology when you're looking at the concept of family trees. So this is one way to kind of hierarchically organize data about ancestry. Okay, so I want to take a look at how conceptually these nodes might be linked together. So I'm going to draw kind of a larger diagram that is just an example of how these nodes may look. So I'm going to ignore the data part in this diagram. I'm just going to draw some nodes. So this initial one, I'm not going to fill anything in for its parent. I'll treat it in a special way that way. And I'm just going to kind of make some arbitrary choices here. I'm just making it up as I go. So I'm going to say that this node that I've created has a left child, and that left child's parent link is kind of the reciprocal reference that points back to the parent. And I'm going to say that it also has a right child, so I'll draw the right child over here. So the right child link will refer to the right child, and the right child's parent link will refer back to the parent. Okay, and I'm going to assume that its right child has a left child. And I'll connect it up, and of course the parent link in that left child connects back up to its parent. I'm also going to assume its right child has a right child, so I'll go ahead and create a right child here. And again, once I created that new node, it has this link that goes backwards. So this is one particular depiction of how a tree may be linked together. And you can see this isn't linear. We can't really meaningfully draw this out in a simple line like we've been doing with linked lists. So you may ask yourself, why are these things referred to as trees? And partly it's based on their typical diagrams. So oftentimes tree diagrams just indicate connections, but not the direction. So in the diagram I just did, I was showing all of the directions and of the links. But here's a common example of a tree. So in this case, it's depicting the individual connections, but it's not showing that this is probably two separate connections, one going down and one going backwards. So this happens to be the little logo that's on the course Canvas site and a few other places associated with this course. So why is it called a tree? Well, the basic idea is if you turn this thing upside down, it looks somewhat comparable to a tree. In fact, a lot of the terminology we'll use is based on the concept of trees and also kind of, in a sense, the concept of a certain type of family tree diagram. So just like a tree, there's some sort of a starting point that represents kind of the beginning of our growth. So the tree, it's at the bottom at the roots. Just like a tree, there's this idea of branching out and spreading out. And in data structures, this is sometimes referred to as the branching factor, the amount of connections that an individual parent may have. Okay, so on that note, let's go ahead and talk about some other tree terms. So the starting point of a tree is very comparable to the starting point of a list. It's some sort of variable that allows us to access the data structure from something that's typically considered the beginning. And borrowing on terminology from biological trees, it's referred to as the root. So in my little example here, this topmost node labeled A would be considered to be the root. The connections, again, are referred to as branches. So this node called A has a left child, a left branch to another node that has a value of A, and a right branch to a node that has a value of T. Children with common parents are considered to be siblings. So as an example here, this node S, its parent is T. This node R, its parent is also this has this value t. They both share this one particular parent. We would say that the nodes S and R are considered to be siblings. Other terminology that comes from the concept of family trees are the concepts of parents and grandparents. So I'm going to pick on this node S here. So the node S, it has a parent with a value of t. It has a grandparent with a value or data of a. Okay. The complement of that is the concept of children, grandchildren. So our root node has two children. One of them has the value a, the other has the value t, and it has a total of 4 grandchildren. So we've got this idea of both ancestors and descendants in our trees. Okay, another important thing is the concept of the height of a tree. So height is about the entire tree. It's a property of the entire tree. I mention that now because soon we'll talk about properties of individual nodes, and there's a related concept. So one way to think about the height is the maximum number of links you can travel from the root to a descendant. So in this tree, it's a pretty simple tree, and the maximum distance we could go is 1 link. 2 links gets us to this T at the very bottom. I could instead go to the left instead of the right, still be 2 links to get me to the D. In this particular tree, we would say that the height happens to be 2. So I'm going to note that over here to the side. Okay. So conceptually, the height is kind of the height. Typically, when we draw out these diagrams, we space them very consistently, and the height is somewhat related to the amount of space it takes on the page. In terms of actual implementation, the important part is really about the number of links we have to traverse. Now, the reason that's important is because oftentimes when we do tree operations, they'll start at the beginning, tip at the root, and they'll travel up and down the tree, possibly. Sometimes they'll also start at a bottom of the tree. So let's think about things that start at the root. If they travel down the tree, we may have to go through H links. Okay, oftentimes the amount of work involved to do tree operations depends on the height of the tree. So for our purposes, what that really means is that oftentimes the big O notation, the things that tell us the upward bound on time, are related to the height of the tree. So we'll come back to that pretty soon. Another related concept is the idea of depth. Depth is actually about specific nodes. Each node has the concept of depth. So the depth is the number of links to the root. So I'm going to pick on the little R node here in the bottom right-hand corner. We would say its depth is 1, 2. It's 2 steps away from the root, so I'm going to write that out as a subscript. Its parent's depth, well, its parent is 1 step up, so you can probably already kind of guess that its depth would be 1 less. But again, it's 1 link away from the root, so I'm going to note that its depth is 1. So what about the root itself? What about its depth? Well, how many links from the root is the root? 0. So we consider the root's depth to be 0. Okay, another related concept is the idea of levels. So levels are kind of a set of things that are at the same depth. So I'm going to kind of divide this tree up. Typically, when we look at tree diagrams on paper like this, or on a diagram like this, they're spaced out consistently and levels are pretty easy to discern. So for this example tree, I may describe the root as being at level 0 or level 1. It's kind of arbitrary whether you start with 0 or 1. I'll go ahead and call this level 0. And then maybe I would say that A and T, which both have a depth of 1, are at level 1. And then maybe the capital D, T, S, and R are all at level 2. So in this case, I'm kind of categorizing level based on all nodes at a particular depth. Okay, degree is also a property of specific nodes. So a degree is the count of the number of children that a node has. So this example tree is pretty simplistic. We'll look at some other trees in just a minute. So we've got several nodes, like the root node, that have 2 children. So we would say that A's degree, the root node's degree, is 2. We've got another node that also contains A. Its degree is also 2. We've got a node that contains a t on the right side that's degree is also 2. And then we've got all these ones at the bottom, and none of them have children, so we would say that they all have a degree of 0. So again, that's a property of an individual node, the degree. Okay, so we'll also do some categorizations of nodes. So again, going back to our diagram of a data structure tree looking somewhat comparable to a biological tree. One of the concepts here is the idea of the extremities of the tree being referred to as leaves. So a leaf is kind of the extremity of the tree. It's something that has no children. It'll have a parent but no children. Sometimes these are also referred to as external nodes. And then there's everything else, all the non-leaves, which are typically referred to as internal nodes. Okay, so let's look at an example tree. So this is an example tree that comes from Wikipedia. So let's pick out some of these terms. So what's the value in the root? So in this case, the root is the thing at the top of the tree here. Its value is 2. Notice that this tree also has another node with the value 2 in it. What's the overall height of this tree? Well, let's do a couple of quick examples. So 1, 2, it's at least 2 because there's at least a path that I have to take 2 links. But remember, it's the maximum or the worst case. So I could go 1, 2, 3. There's another one that's 1, 2, 3. And again, kind of based on the way that this is drawn on paper, we could kind of say, oh, well, 1, 2, 3. We could just identify the different levels visually pretty quickly. Okay, so root's value is 2. The height of the tree we would say is 3. What's the degree of the node containing 9? So that's over here. It only has one child, so its degree would be 1. Okay, what's the degree of the node containing 7? Take a second. It's connected up to 3 children, so its degree would be 3. This is a different sort of tree than the simple example we've been looking at. What's the degree of the node containing 5? Which one? So there are 2 nodes that contain 5. This one has a single child, so it'd have a degree of 1. This one has no children, so it'd have a degree of 0. What are the leaf nodes? Okay, so let's go ahead and circle everything that'd be considered a leaf node. So leaf nodes are things that have no children. So this doesn't have any children. This doesn't have any children. This doesn't have any, this doesn't have any, and this doesn't have any. And just to check, I'm going to quickly look at all my others. So our node 2 here has 2 children. Our node 7 has 3 children. Our node 5 has 1 child. Our node 9 has 1 child. Our node 6 has 2 children. So the leaves are 2, 10, 5, 11, and 4. The specific ones that I've circled. Okay, so what about the values of nodes on the same level as 10? Well, so again, we can kind of break this down and identify where the 10 is at. And 10 has a depth of 2. So everything that has a depth of 2 would be considered on the same level as 10. In our diagram, we can just easily visually pick out all of the nodes that are on the same level as 10. Okay, so why trees? What's good about trees? They provide shade. They're great oxygen generators. Let's talk about data structure trees maybe instead. So one of the things that they're really handy for is organizing hierarchical data. So the way you organize files on your computer is based on a tree. Folders are nested in other folders. There's a hierarchy of organization. As we look at trees later on this semester, you'll get a better sense of how that actually works. That's just one example. Oftentimes trees are faster than their linear alternatives, and that's what brings us to trees right now. If you remember, we had some deficiencies with our various attempts at priority queues. We're going to try and fix some of those by using trees. So we're going to focus on specifically binary trees for the time being. So binary is in 2 options. So binary trees have at most 2 children. This also brings us back to the concept of degree. All nodes in our tree have a degree of less than or equal to 2. If you remember, one of the example trees we looked at, the one that came from Wikipedia, had one node with 3 children. That is not a binary tree. In our case, we're also going to put some restrictions on the shape. We're going to restrict ourselves to shapes that are considered to be complete. So let's drill down and look at what complete binary trees actually are. The basic idea is a restriction on how the binary tree has to be built and the overall shape that it has. All levels up to the last level are filled, and the last level has nodes as far left as possible. So it's about shape. And really there's a kind of a simple way of kind of picking out shapes that are considered valid. So one of them is the kind of perfect pyramid shape. So trees where they kind of fit this picture. Also, if we have something that's a perfect pyramid up to the last level, and the last level is filled in from left to right, but maybe not completely full. So I think of this as being either the perfect pyramid or the jagged pyramid, where the bottom right corner, the very bottom right corner of the pyramid may be cut out. There is a similar concept that we'll also be using, a full binary tree or a proper binary tree. So the concept of being full or proper is about internal nodes, non-leaf nodes, having 2 children. So let's look at some example binary trees. First, we'll focus on the idea of complete binary trees, and then next we'll come back and look at this idea of being full or proper. So remember, the idea of complete is really about shape. Perfect pyramid, jagged pyramid. So we've got 3 example trees here. Which ones are considered to be complete? The example we started off with, our class logo, is in fact a complete binary tree. What about this next one? So gosh, if for this to be complete, it would have to have some more nodes filled in here. This one doesn't have quite the right shape we want. This last one, well, so the first layer is full, the second layer seems to be full, the third one seems to be full. This kind of has that jagged shape that I was talking about. By the way, the right 2 diagrams are also from Wikipedia. Okay, let's come back to this notion of full. So if you remember, the idea of full is that nodes either have 2 children or no children. So we have all internal nodes that have 2 children or no children. So let's look at that. So again, our class logo, A is an internal node. It has at least 1 child, and in fact it has 2 children. So good so far. The second node that has a value of A also has 2 children. T has 2 children. D is a leaf node. It doesn't have any children, so that's good. That's okay. T doesn't have any children, neither does S or R. Okay, so we would consider a class logo to also be a full binary tree. What about this next one over? So the root node has 2 children. Its left child has 2 children. Its right child has no children. That means it's a leaf, but that's okay for a full binary tree. This leftmost node is a leaf. That's okay. This node right here has 2 children. That's fine. And these both have 0 children. Okay, so that's all good. So this was also considered a full binary tree. And now the rightmost one. Now, I'm going to kind of cut to the end here. We just have to find one counter example, one thing where a node has, it fails to have either 2 children or 0 children. So I'm going to pick on this node right here. So that's an internal node. It has at least 1 child, but it doesn't have 2 children. So this last one would not be considered to be a full binary tree. Okay, let's go back to the concept of complete binary trees. For the time being, that's going to be slightly more valuable to us. So I want to talk about the idea of building a complete binary tree. So conceptually, they're kind of built from left to right, top to bottom. So I'm going to go ahead and think about some example shapes for complete binary trees. So first of all, what would a binary tree with just 1 node look like? Well, that's kind of simple. It's just a single little circle. So that would be a a valid, complete binary tree. What if we have 2 nodes? Well, I have to build things in the proper order. So I would have my root node, so I've filled up level 0, and then I need to start building level 1 from left to right. Okay, let's move on. Let's think about a complete binary tree with 3 nodes. So 3 nodes, I would have my root node, and I would fill my tree from left to right. So you notice these are basically just building. We went from our root node to a root node plus a left to a root node with the left, and then we added a right to it. We'll go ahead and add on a few more examples here. So let's look at a complete tree with 4 nodes. So we left off with a complete tree with 3 nodes. So root, the root had its left and its right, and the root's left would also have a left. So that gives us our 4 nodes. 5 nodes, we'll just take what we just did and build off of it. So I'm going to take that exact same shape, I'm just copying it down, and then on our bottom level here, we'll fill in from left to right. Okay, you get the idea. If we were to continue with this tree with 6 nodes, we'd just continue to build on, and 7 nodes would build on, and so on and so forth. Okay, so let's try and identify some relationship between the height of the tree, which remember will probably relate to the amount of work we need to do sometimes, and the number of nodes and the number of leaves. So I'm going to build a little table here. We'll think about the height of the tree, the minimum number of nodes, and the maximum leaves and the maximum nodes at that particular height. So height of 0, so that could be 0 nodes or 1 node. This is the one place here where I'm going to be just a little bit sloppy. I'm going to assume our tree always has some data in it. So I'm going to draw a little diagram over here on the top right. So right now with a height of 0, that could just be a single node. That single node is also a leaf node, so our min nodes and our max nodes and our leaf nodes are all the same. Now let's think about what happens if we have a height of 2 in a complete binary tree. Well, we know that this is kind of the first example that we get to with a height of 2, adding a left child to the root. So at a height of 2, at the very least, I have 2 nodes. But if I continue to fill this in, I could have a total of 3 nodes and still be at a height of 2. At this point, I've filled up my level there. So it's possible once we get to a height of 1, I have at least 2 nodes, but at most I have 3 nodes. And currently the maximum number of leaves I have is 2. Okay, so building on to this tree is now kind of filled up. So to get to another level, I'm going to have to add a new node on, and I'm going to have to do that kind of working from left to right. So at this point, I've now got a total of 4 nodes, and that just barely got me to a height of 2. Of course, if I wanted to kind of fully fill this out, I would fill from left to right, and I'd stop before I actually end up adding a new level. So at a minimum, at height 2, I've got 4 nodes. The number of leaves I might have at the moment is 4. That's kind of my maximum number of leaves. And the total number of nodes in the tree is the 4 on the bottom, plus the 2 above that, plus the root, so a total of 7. I could extend this one more layer. So to get to my 4th layer, a height of 3, I now have a total of 8 nodes. My maximum number of leaves is, if I fill that layer entirely in, starting to run out of space on my diagram here. A total of 8 leaves is possible, and if I count up all of the nodes there, it's 15. Okay, one of the things I want you to notice is there's a relationship here. At the moment, I've got a total of 15 nodes in my tree. To get to another height, I'm going to have to add one more node onto this. So the maximum number of nodes in one height can be used to find the minimum number of nodes in the next height. I basically take that maximum, add 1 onto it, and I get the minimum number of nodes at the next height. Okay, so that's a really important relationship that we can take one of these and add 1 and get to the other one. That also means that we can go backwards. So we have the minimum number of nodes, we could subtract 1 and find the maximum number of nodes at the previous height. Okay, so let's try and generalize this. Let's think about how this is going to play out when we get to layer n. or layer h rather. So we'll think about h as being a generic variable that represents the height of our tree. And if you notice, there's a pattern here. When h is 0, our minimum number of nodes is 1. When h is 1, it's 2. When h is 2, the min nodes is 4. When h is 3, the min nodes is 8. So you've probably already guessed that basically this is increasing powers of 2. So we could represent the min nodes as 2 to the h. And you may have also already noticed that the minimum nodes and the maximum leaves are also the same value. Okay, so let's try and figure out the maximum number of nodes. And that's where I'm going to come back and utilize this relationship. So if you remember, we identified that the maximum number of nodes, we can add 1 to that and get to the minimum number of nodes in the next layer, and we can go backwards. If we know the minimum number of nodes in the next layer, we can subtract 1 and get the maximum number of nodes in the previous layer. Okay? So if we're at layer h, the minimum number of nodes in the next layer would be 2 to the power of h plus 1. Subtract 1 from that, and we've got the maximum number of nodes in the preceding level. Okay, so we've got some general formulas that give us an idea of the number of nodes versus the height of the tree. So we'll use that to our advantage. So a general theorem that we'll depend on for a while will tell us the total number of nodes in a complete binary tree based on its height. So a complete binary tree of height h has between 2 to the h and 2 to the power of h plus 1 minus 1 nodes. So there's a corresponding lemma that we can use too. So the lemma is a complete binary tree of height h has a maximum of 2 to the h leaves. So we saw this by example as we were building the table, and we kind of observed what the pattern was and came up with a formula based on observations, but that's a little bit short of actually conclusively proving it. So let's go ahead and work towards an actual proof. So we'll do a proof by induction. I'm going to focus on just the lemma, the second part, the number of leaves. So we'll start off with the base case. So again, we're trying to prove that a tree of height h has a maximum of 2 to the power h leaves. So base case is when h is 0. So our base case we can just demonstrate by example. So a tree with at most a single node also has a leaf. And so the thing that we're trying to prove is that 2 to the h, a complete binary tree of height h has 2 to the h leaves. We know just from the definition of our trees that a tree of a single node has a height of 0, and that node is also a leaf, just by the definition of what a leaf is. Okay, so that's our base case. We've kind of established that a single node will have a height of 0 by definition, and it will be considered to be one leaf, which is the maximum number of leaves you can have at that height, just kind of by the definitions. Our inductive hypothesis will suppose that a tree has a height h and has 2 to the power of h leaves. So we're proving by induction. We're going to assume that what we're trying to prove is true. So we'll show that a tree, our goal is to show that a tree that is 1 taller, height of h plus 1, has 2 to the h plus 1 leaves at max. Okay, so that's our goal. So we'll extend our complete binary tree of height h. So imagine that we've got our tree here, and I'm just going to draw it as kind of this generic sort of triangle. And it's got a total height of h. And we're going to add one more layer onto the bottom of it. So let's extend the complete binary tree of height h to be a tree of height h plus 1. Okay. We're already assuming that there are 2 to the power of h leaves in the tree of height h. Each of those leaves can have 2 children. So our bottommost layer here is capable of having twice as many leaves as the preceding layer. Okay, so it's 2 times 2 to the h. Simplifying the equation there, we get 2 to the power of h plus 1. So essentially we've demonstrated that by induction, that if a tree of height h has 2 to the h leaves, that a tree of height h plus 1 is capable of having 2 to the power of h plus 1 leaves. So our original theorem, in addition to the lemma we just proved, was about the height of the tree versus the nodes in the tree. So there's a relationship between n, the number of nodes in the tree, which is oftentimes what we really care about in this course, and h, the height of the tree, which is sometimes necessary in order to figure out the time complexity of various operations. So for complete binary trees, and remember this is specifically about complete binary trees, where they have this particular type of shape. We've got this relationship that n is greater than 2 to the h and less than 2 to the h plus 1 minus 1. Okay, so again, we're often focused on n. We want to express h relative to n. So let's take a look at that equation, and we'll try and get this to give us some relationship of a clearer relationship of h and n. So let's express h relative to n. So I'm going to focus on the left part of the equation first. So it was 2 to the h is less than or equal to n, and I'm going to turn that around. I'm just going to read it backwards. N is greater than or equal to 2 to the h. I'm going to take the log base 2 of both sides. So using the properties of logarithms, we'll find out that the log base 2 of n is greater than or equal to h. Okay. And again, I'm gonna read this backwards, so we have a relationship of h. So h is less than or equal to the log base 2 of n. So I've taken a look at this left side of this equation. Next, I'm going to take a look at the right side of it. So again, we're trying to express h relative to n. So we can kind of come up with an upper bound here. So I'm going to take n. So again, n is less than or equal to 2 to the h plus 1. That's my equation, but it's got this minus 1 out there that's kind of hard to deal with. But you know what? I can kind of ignore that and just focus on 2 to the h plus 1. This is strictly less than this. Okay? So I'm going to break this down and just focus on n being less than or equal to 2 to the power of h plus 1. So we've got the transitive property of less than or equal to, so I can simplify and kind of ignore this middle part here and get rid of the minus 1, just so it's a little bit easier to work with. So taking the log base 2 of both sides, again, we'll find that the log base 2 of n is less than or equal to h plus 1. Again, I could kind of read this backwards and come up with a relationship relative to h. h plus 1 is greater than or equal to the log base 2 of n. And I could subtract 1 from both sides and come up with h being greater than or equal to the log base 2 of n. Okay, now we've got these two different parts that we've developed from the two different pieces of our original inequality relating n to h. Let's go ahead and combine those two parts together. So again, part 1 and part 2, and we'll just join them together and put h in the middle. So we know that h is greater than or equal to the log base 2 of n minus 1, and we know that h is less than the log base 2 of n. Okay, at the end of the day, what this really means is that we can say that h is big theta of log base 2 of n. In this class, a lot of times we'll just say log. I've been repeatedly indicating the base of the log. And the base here is good to know. We were working with binary trees, which is partly why we have these relationships, why 2 pops up all over the place. For much of the rest of this unit, I'll probably just read this as log instead of log base 2.